Welcome back, folks. We're still working with Thevenin's theorem. I want to give you an example, kind of worked end to end. All of the videos up until now were that one example, and I was introducing all of the methods and whatnot. I want to work one problem end to end and show you how it's done, because that's what you're going to have to do. Okay? So I got a good one picked out for you. Here we go. There it is, right up there. Let's see, how can we do this? So I jokingly said the steps to find a Thevenin equivalent circuit were find V Thevenin, find R Thevenin. That's exactly what we're going to do. Okay, so let's see. Find V Thevenin for starters. Now, this problem is stated the way that I've seen textbooks state the problem. You may also see it on the FE exam. Find the equivalent circuit between nodes A and B. So what's implied there is that the load will be connected here. Okay, but it wasn't drawn. So that's why in every video prior to this about Thevenin's theorem, I said remove it if it's drawn. Okay, in this case, it's not drawn. So we don't need to remove it. The load will be connected there. So just pay attention to how the problem's stated. Realistically, I'm going to have a coughing fit now. But why would I take that out of the video? Okay, so realistically, you're going to have some context. These are textbook problems. If you're doing this type of work, you're going to understand the context in which you're doing this analysis. You're going to understand that you have maybe a generator and you're plugging something into that generator. Well, the thing that you're plugging into it, that's the load, and the generator itself is going to be the fixed portion of the circuit. Coming out of textbooks, coming out of videos like this, we don't have that context. So when we're taking exams, I usually say, come ask me if you're unclear. I try to state it as clearly as I can. I will give you that context. In real life, you should have some understanding of what portion of the circuit is fixed and what portion of the circuit is changing. Okay, everything we see here is the fixed circuit, and we got to find V Thevenin. We're going to do that by finding V open circuit. Okay, so what we're really after is V open circuit. So we've got to do some analysis here. There's a dependent supply. They're not going away, so I hope you're getting comfortable with them, because they do come into future classes. We've only got one, let's just call it I. We've only got one mesh. Okay, it's over here. This is not a closed path. So we've got to do our analysis based off of that, but we've got a dependent supply in there, so we got to be a little careful. We can do that. We're going to go the long way, right? So we go up 12, we go down 4 times I. We go down 2ix. And we go down 6i. And we're back to where we started, so that's equal to 0. Okay, we've got one thing that needs to be dealt with there, but it's nice and simple. Does I touch ix? Yes, and it goes in the same direction. So ix is just equal to I. So we can get rid of that control variable nice and easy. I'm almost tempted not to write it again, but I know better. Right, minus 6i equals 0. Then we just got to solve for I. We got one equation, one unknown. We can solve this, no problem. Okay, so negative 12i. 12 minus negative 12i equals 0. So 12 equals, oh wow, this is, we can handle this. Look at this, I is equal to 1 amp. Nice and easy. Okay, what we're interested in is V open circuit. I should have drawn that from the get-go. There's V open circuit. So if I want to find V open circuit over here, then I have to write some KVL. And I can write the KVL. I could write it all the way around, but I am lazy, and that has more terms. I can just as easily write the KVL around here. Okay, as long as I know all the voltages. This one has no current flowing through it, so that's going to be 0 volts because there's no mesh there. This one, well, now we know it's 1 amp, so let's say this is V6 ohm, and V6 ohm is going to be I times 6 ohms, or 1 times 6, which is 6 volts. Okay, so writing this KVL, all right, in green, we go up 6 volts, we go down 0 volts, and we go down V open circuit, and that's equal to 0. That drops out, solve for V open circuit, and we find that it is 6 volts, and that's equal to V Thevenin. Okay, halfway there, behind my head. 6 volts, V Thevenin. All right, find V Thevenin, find R Thevenin. That's our next step here. Okay, so find R Thevenin. Okay, let me grab a fresh copy of the circuit. There it is. We'll put it over here. We'll put it right there. I think I'm happy with that. Okay, I can't use method 1, right? There's a dependent supply. I can use methods 2 or 3. They both handle dependent supplies, no problem. And there is one independent supply. So I could still use method 2. That's what I'm going to use. I'm going to use method 2 for this one. We will have an example where you're forced to use method 3. Method 3 is going to work too. And if you go look at my notes, I believe it's in my unedited notes that I posted along with these videos. If you want to see that it's consistent. It's consistent. Okay, so method 2 says remove the load if it's there. It's still not there. And find I short circuit. So I'm going to short where the load would be connected. I'm going to make that go down. Okay, and that's I short circuit. Now I got to find that any way I want. And the way I want is to use mesh. Maybe I should do nodal. You could do nodal. It would work just fine. But if I'm finding a current, using mesh is usually a little easier. I'm also just more comfortable with mesh. Okay, so let's see. It's going to be a 2x2 now, so it's a little more complicated. But we still have this dependent supply we got to work with. Remember to make your analysis separate. Do not reuse any value. Do not reuse any expression. IX is no longer I, right? Because I have a completely different circuit. So build that firewall, right? Don't go above that point, above that line when looking for values. Keep it clear in your head. Okay, so no current supplies, so 2 KVLs. This is going to be my KVL for I1. I go up 12, I go down 4, I1. I go down 2 IX, and I go down 6 I1 minus I2. And that's equal to 0. IX in this case is different, and that's why I said build that firewall. Okay, don't go use IX up there. IX, does I1 touch it? Yep, it goes in the same direction, so it's positive I1. Does I2 touch it? Yep, it goes in the opposite direction, so it's a negative I1. Now I've got to plug this in for IX here. And I'll distribute some stuff just to get us moving. Okay, so 12 minus 4I1 minus 2I1 plus 2I2 minus 6I1 plus 6I2 equals 0. Okay, so I plugged this in, I distributed the 2. Don't forget to distribute the 2. And then I distributed the 6. Grouping like terms, let's see what we got here. We've got I1, I1, and I1. So that looks like negative 12 to me. Negative 12 I1. And then what do we have for I2? We've got positive 2 and positive 6. So that's positive 8 I2. All right. That 12 needs to move over to the right-hand side, so it is negative 12. Whew. 1. Done. Not too long, right? Shortcut's a lot nicer. Speaking of the shortcut, why don't we use it over here? There's no dependent supplies that come into play around using the or writing the KVL for I2. So let's go ahead and do that. And let's see if I can do that up here in this space. KVL for I2. Okay, what does I2 share with I1? It shares the 6. All right, so that's going to be negative 6 I1. And then what does I2 touch? It touches 9 total. And there are no voltage supplies. Okay, so I did the shortcut, but I wrote it out as an equation just to be consistent between these two. But it still works. Check it out. Give it a try. Hopefully you get the same answer. Okay, solving that system of equations, I could put it in matrix form. I'm hoping you're comfortable doing that by now. If you're not, please go review some videos. Negative 12, 8, negative 12, negative 6, 9, and 0. And I get, let's see if I can squeeze it in here. I don't want it in blue. Let's do it in white. I1 is equal to 1.8 amps. I2 is equal to 1.2 amps. Okay. Okay. And we find I short circuit. I short circuit is equal to I1 doesn't touch it, I2 touches it and goes in the same direction. So I short circuit is just I2, or 1.2 amps. Okay, so that's another good result right there. We have V open circuit, we have I short circuit. Let's calculate our values. Calculate our Thevenin. Okay, so our Thevenin is equal to V open circuit over I short circuit. V open circuit in this case was 6 volts. I short circuit is 1.2 amps. Volts over amps is always going to give us ohms. And we find we have our Thevenin is equal to 5 ohms. Okay. Now, if I had to draw the Thevenin equivalent circuit, we get a voltage supply. We get a series resistance. This is our Thevenin. And now we know that that's 5 ohms. This is V Thevenin. And we know that that was 6 volts. Okay, we got nodes A and B. Anything we connect here is going to say the same voltage, the same current, and therefore the same power as if we connected it up here. Okay, which analysis would you much rather do? I would rather look at the voltage divider and a little bit of Ohm's law using the equivalent circuit, rather than having to come back and every time I swap out a load, go through this analysis with a dependent supply. So that's the power of Thevenin's theorem. All right, I got another example. This one's going to force us to use method 3, so you know what that means. And then we'll look at a slightly larger example where we take 2 big circuits and we find both of their equivalents and we glue them together. So that should be fun too. Okay, that's where we're headed. Stay tuned and good luck.